Okay, first of all, thank you so much for attending me during this presentation. It's my pleasure. I'm Mosab, a PhD eventually candidate here in our department of computer science. Today we want to talk about several state-of-the-art fine-tuning approach that I think they are really useful for academia, because we have a lot of problem with the resources, with the GPU, with the number of the parameter that we can handle it with our resources. So I think it's really necessary. And another thing is one of my current project that we try to solve training the GP3 to train our model. Okay, so let's go ahead. We have this 3.1 LoRA adapter, then QloRA has been published, and after that DoRA, and you can see this timeline here. And here you can see their citations, 30,000 citations from 2022, shows how much this model is useful and popular in academic area. These are papers. Some of the resources you saw on the bottom of the page, and some, if you are interested in one of those techniques, I uploaded some videos that I use some of them, and you can go deeper in their detail if you're interested in each of these techniques. Okay, first question is that what is the fine-tuning and what is the differences between fine-tuning and transfer learning? So since we don't have some student that expert here in that in our department and enough attendance, so I answered this question by myself. Fine-tuning and transfer learning. Transfer learning means you have a trained model, which we call it pre-trained model, and we use exactly the same weight in other tasks as a base model. For example, you have a BERT model, you generate a vector for a sentence, and use those generated vector for some task, like training regressions, okay, training a SVM to do another task. But in fine-tuning, it means during the after pre-training, after using the pre-trained model, you at least train a portion of the parameter in these models. It can be, if you have a pipeline, for example, there are some blocks in your model, for example, BERT. If you train, if you train the whole model, which means full fine-tuning technique, it can possible to train only some layer of the models. It can possible to train only the last layer or beginning of the models, or also you can train the prediction layers of the model. All of them will be considered as a fine-tuning. So fine-tuning is really expensive in many reasons. There are some techniques that offered with the researcher to solve this problem, to save your time and your expenses to training these models. Here you can see in a traditional way for some tasks like summarization, like table to text, like translation, people train most of the weights during the fine-tuning process. But in this paper, that you can go through that paper, prefix tuning techniques, they offer we can add, maybe it's surprising for you, but we can add several blocks at the beginning of the BERT model, for example, which fine-tuning for your task to train the model in a specific task that you want. And you can see here comparison between this technique of the fine-tuning with the full fine-tuning technique in blue score area that shows how much with the bigger data set you can achieve higher accuracy. But it's not solved the problem of energy and accuracy. Another interesting technique that was really popular in some days was adding adapter to your model. Here we have a BERT cell. When you train the BERT model, we have several these BERT cell. During the BERT cell, instead of training the model, we freeze all the weights and we add some adapter to the model. This adapter structure, as you can see, it's similar to the encoder and decoder, which have some kind of bottleneck, and only you train this small portion of the adapters. So to remember all the technique that we use, let me write the adapter here, the first one, before going through the LoRA. So we have the adapter techniques. Let me say another thing I forgot to mention, that the problem is here, when you add this adapter layer between the layers, it means you need to spend more time to generating inferences, because this layer has been added during your generation part. So it's, again, maybe the number of the parameter that you train decreased, but the time of generation will be increased. So let's go to another technique that need to be familiar before going to the low rank, before going to the LoRA. One of the interesting idea, not only for this one, but also for all of them, is that with simple mathematics, you can do a lot of achievement in your project. For example, here we have such a thing that we call it a low rank adapter. What that means? What's the rank of the matrix? The rank of the matrix is that you have how many independent column or row you have in your matrix. For example, we have here 1, 2, 3, 4, 5. The second, which is independent totally because there is no column before that. Then we have 3, 2, 4, 3, 4, which is independent because you can generate this one by using this one linearly. But look at this one, 4, 4, 7, 7, 9. You can generate this vector by these two vectors, multiplying 1 to each of them, and then add each row together. So you can generate this one together. And here you can, for example, multiple 0 to this vector, and multiple 2 to this vector, and generate this vector. And again, same for this second vector. So it seems we can regenerate all these columns only with these two columns. We call this matrix as a low rank, the rank 2, which means we can regenerate it by only using this structure, 4 by 2, 2 by 4. And what's happened here? At the beginning, we have a n by n matrices. Okay? So here we have a n by 2 multiple by 2 by n. What that mean? That means you use fewer parameter to regenerate a similar structure. Here you have 5 by 5, it means 25 parameter. Here you have only 10, 2 by 5, and here you have only 10, and generally you have 20. You save memory. Imagine an increase in exponentially, how much space you can save. So using the low rank technique in the regenerating the matrices help you to save the space. But how these stuffs can help us? Let's go forward. Okay. In general, in text generation, we use this formula, and we are looking for that one. It's our goal, our likelihood. What's that? It means predicting the y, which is our token, which can consider as a word, predicting the word y based on generated sentences, generated token before. For example, I'm playing is a vector here. Football or soccer or anything should be predicted here. We try to increase the possibility of those targets that we expected. Not only for all the token in sentence, but for all the sentence in our data set. It's what we are looking for, and the maximum number will be 0 because here we have log on the probability. What's happened in the LoRA? They said, okay, let's do another thing. Instead of increasing the value here based on the parameter on our matrices, let's put the pressure on a low rank data set. So instead of changing this parameter, which we will change in, we fine-tune only a small portion of the model. Then we increase again the value of this formula, which will be 0. So what you said, sorry? T here is a number of the token, which means y is a target, x is a predicted sentence. For example, let me show. X, for example, is I am, Y should be, for example, Mosab. So, and here we want to predict the T based on all these values that we have. The weights and YT. T is here, it's 0, it's 1, and T for me is 2.
Based on X, why you want to base it on Y less than T?
Okay, we have X, I am, and we have T. Just a second. We have T number 1. Okay, because we here is our previous generated sentences. Okay, it's our previous generated, which all of them as a tuple. Okay, is as a couple. You have, for example, here I. For example, I. What was the next word predicted will be am. Okay, so if I want to predict Mosab, I had predicted I based on M, which was the target for M, for Y that has been generated.
So I is Y1, M is Y2, and Mosab is Y3.
Yeah.
Then why would X, what is X is the ground truth? Oh, X is given part, so then given before.
Yeah, X is the input, Y is the predict, what we want to predict, and T is the number of the token. But let me.
Then X is not I am, right? X is something happened before.
Yeah, exactly.
Yeah, I got it.
We want to predict Y based on predicted words before the next prediction. Yeah, but we can go through that after the presentation to make sure I understand your question and I understand this formula correctly. Okay, so based on that, we talk about that this probability goes on the weighted matrix of weights. Now we want to push push the model to only use the low rank matrix instead of the whole weighted matrix, which means, which is what LoRA used here. Okay, let's go through the details. In the forward pass, we have a vector X, we have a weight matrix, and we have a hidden layer, which is the embedded vector. Okay? They said instead of, let's assume this is a low rank matrix, which means we can reconstruct this one with a low rank structure, with two smaller matrices. So imagine we have here n by n matrices, which is our weight. Is it possible to regenerate this matrix n by r and r by n? Is it possible to reconstruct this one? It's their assumption, and they show it's possible. An interesting part is that sometimes they show it's possible to use the r equal to the 1, which help you to save a lot of resources, a lot of weights. We have previous weight 0. During the back propagation, you calculate the delta W, which means how much each weight need to change. They said instead of training this one, let's training this one, B by A. A is one of the matrices, B is another one. So during forward, we go through this direction. During backward, we go through this direction. The initial weight is 0 here and is based on normal distribution. During the forward, in each step, during the forward, they multiply these two matrices to each other and add one by one cell by one cell to these matrices. So here, all the weight is 0, multiplied by each other, whole the matrix will be 0. 0 will be added to this matrix, nothing change. They generate something, calculation will be done, Then backpropagation says how much they need to be changed. We only change these matrices. In another step, again, we add this stuff and so on. So we can repeat this structure several times based on number of epoch or iteration that we have. Okay. Here we have attention structure. We don't want to go through the attention.
Can you go back to the previous
Sure.
slide? So previously, the delta W can be calculated by using backpropagation.
Yep.
And now, how do you calculate the B times A?
Here, the multiplication was these two matrices is exactly same size as this one. So when you backpropagate the error, you can, instead of updating these weights, updating these weights, updating the values here because they are the same and freeze this structure. Like when you backpropagate the error during the fine-tuning, you freeze several weights. In this structure, they freeze the weights and offer changing another weights. I will show it in next slide. Okay. So we have attention mechanism here. And the interesting thing is that to make it, I hope this one answer your questions. Okay, we have here a block of BERT, you can see, and in each input of attention is Q, K, and V, the several matrices. They try to train those matrices. Imagine we have matrix Q here, matrix V here, and matrix K here, okay? They said instead of the, let me create a whole structure. Okay, Q, K, and V. Okay, what they said let's use the low rank matrix for each of them, okay? So we can construct such a thing for all of them, okay? I don't want to spend all the time on drawing. Imagine it's low rank matrix. During the forward, and it's happened for here again and for all layers. When you wrote a sentence like I am, you expect to generate, for example, my name. During the backpropagation, they freeze these weights and direct the error to all these matrices, like that. And they freeze these stuffs and bring back whole models. When these weights updated, when they update these weights, finally, they simply multiply each weight to each other and add them easily to related vector. So we don't have any adapter during the generating sentence. They didn't add any layer. They didn't add anything. They also trained a small portion of the weights here and changed the whole matrices during the generation phase.
So after the model has been trained, those low-rank matrices will permanently be there. There's no way to merge them together.
Look at here, for example. We have VQ, V here, okay? There are three matrices here. They said they create another line to add another low-rank matrices.
But those other matrices will keep there, will remain there.
Yeah, they will be remain during the process of the training, fine-tuning. After finishing the fine-tuning, they eliminate this structure because we didn't need those stuff. We use those information to update these weights. Let me say something. Here, for example, I draw it, it's really bad. This structure is the last one, okay? We have a multi-layer attention cell here, okay? What is inside the multi-layer attention? Three matrices, K, V, Q, okay? They are n by n matrices. Now we have another n by n matrices we generated by the low rank. Because the low rank can multiply to each other and create another n. Okay.
But the weights, I mean, the matrix for the weights will always be there, right?
The values inside the matrix.
Not the values for Q, but the matrix A and matrix B
Okay.
will always be there, right?
Only during the fine-tuning process.
How do you get rid of them after you got A and B? How do you merge that with the
When we design a model, we create a sequence by sequence information and we pass the data. During the forward pass, model doesn't know there are such a thing. Because during the generation phase, before going to the fine-tuning phase, during the generation phase, model only see these matrices because before coming input during these matrices, this information has been added to those matrices with another function. These matrices has been updated. Okay, model doesn't know anything about this structure. It only goes forward. During the backward, during the fine-tuning, we add the information, we freeze these stuffs, and we define, they define a pass to these matrices. Only these matrices by a mathematical computation can be calculated because we have the input, we have the output, we have this one, so we can calculate the derivation. So we can update these weights. When we update these weights through the first layer, the fine-tune of the first phase of the fine-tune has been done. So again, we want to regenerate something. Again, we have those stuff that can be added without anything that, without the input hasn't any information about these stuffs again, because it's processed repeated again, like the first time.
What do you mean? The data has to go through those layers generating values?
Exactly like the first time. Input vector goes through this vector without knowing anything about these stuffs.
So what are those contributing to the?
What's their contribution? Their contribution is that for the first time, we have a zero and normal distribution initialization for these vectors. So the first time contribution adding to this vector do nothing because they are zero. Okay, and we do the summation. Just a second. They are zero. After the first fine-tuning, their values change. Before generation, they add this changes value to their matrices, related matrices. So we can interrupt this connection. Sorry if I couldn't explain it in a way that would make it more clear.
So the data do not need to go through A.
Exactly. Data doesn't use those information. Data only see the V, K, and Q because they has been updated before seeing the data.
Oh, okay. A and B is estimated for delta W.
Exactly.
Okay.
Exactly. Yep. Okay. So here let's see their result. The model is Roberta. Next slide is GPT. We go through that. The Roberta with the fine-tuning, full weight fine-tuning has 1.25 million parameter, but LoRA only train 0.3 million parameter. Just compare the number of the weight that you train during the fine-tuning and look at the result. Most of them shows similar result, even better in such tasks. It's really interesting. I don't know why, but they show with only training smaller portion of the weights, lower. It's not accurate if I said you train a small portion of the weight because all the weights is changed. We only train a small low-rank data set and multiply them to each other, then re-change every weight that we have in the Q, V, and K. So you can see here how much their accuracy are similar or even better than the fine-tuning the whole of the model, all of them. Another interesting thing that they show is that when you have a bigger model, you have a more accurate result. But I think, for example, here, Roberta has 3 million parameter. They has 90%, exactly similar to what they have. Here is GPT-3 with a huge number of the parameter and only training by, this one is adapter. If you remember, there was a technique that adds some block during the fine-tuning models. But you can see LoRA with only 4.7 million parameter shows similar performance to the GPT in several tasks. In MNLI, they show better result. And I think it's really interesting. At least for me, it's really worked because when I trained the GPT-3, the open source version of the GPT-3, always my memory crashed. And I think this result shows how we can save the resources. Here is another result, but I can skip it to save time for the other two one. I strongly suggest to go through the paper and see all their results. They show how much by using the low rank matrices you save the, by the it's same as a low rank, but they show how much decreasing the number of the parameter save the accuracy during the using the LoRa technique instead of the other fine-tuning technique. And full fine-tune is only 1 point because you train the whole portion of the parameter. And it's really amazing that you can see with rank 1, which is 2 vector, only 2 vector, you mimic the whole weight of the matrices. And it's wonderful for me. I don't know how you look at that, but it's really amazing that with 2 vector you can mimic the behavior of whole of the model for each matrices. And you can see even you can get better result by training different matrices. Yep. Okay, let's go through the QloRA model, which another update version on the LoRA. Again, they use another simple mathematical knowledge to improve the fine-tuning here. Quickly, we have quantization. Every time, if you want to save a number, without quantization, you can't, because for a single number, you need infinite. Imagine you want to save the p number. It's impossible because there are infinite value after the point. So we need to do quantization. For example, by like an integer one. We have integer technique, integer quantization here, but sometimes it's not enough. For example, if you want to talk about the author, you say, this author belongs to that decades. We don't need those information. Sometimes quantization help you to reduce the amount of the information that you save, but save with the same accuracy. Another interesting thing in weights in machine learning is this graph that shows when you train a model, you have a matrix, okay, full of weights and information. When we draw the histogram of these weights, most of the time we saw majority of the value are around this peak. It's really clear, Their normalization is normal distribution. Their value follow the normal distribution, so it's really clear the most of the value is here. If you want to save the amount of the space that you have, you need to quantization. But imagine you do quantization without considering this knowledge in your weights. Most of important weight that you have only will be replaced with similar value, which is awful. So you need to be aware about the number of the value that you have in each portion. It will be, I think they call it wise block quantization or something like that. So it's wise blocking. Now we have double quantization. Double quantization. What they did, they said, okay, If we do that, it's not enough. Sometimes the differences between these numbers is really difference between these numbers. So they said, let's normalize this value, then do quantization again to save, to decrease the effect of outlier on your data. For example, here we have this 4 number. They create the first chunk and then do blockwise normalization because the maximum value is here is 3.1 and here is 1.2. Then do the normalization, then apply the quantization in this area. So it's the quantization formula that for if you want to move your number to another space. You only need to multiply your number by in this portion, which is the maximum number in your area, by the maximum number of the area that you want to move your number and the maximum number that you have. Another thing that I didn't understand it well is they apply a hardware technique, which I didn't know that, and I'm not really familiar with that area. They said we use the space by moving the data from the GPU to the CPU during the fine-tuning phase. I don't know how they did that, but they mentioned it was our novelty when the GPU is full. They pass the data during the fine-tuning to the CPU and like a queue, and then bring back the data to the GPU for calculation. It's one of their novelty as well.
You don't really move the data from GPU to CPU. CPU does not save data. You are moving.
Sorry, for calculation, not for saving the data.
Yeah, you are actually moving from VRAM to the
Yeah.
RAM. RAM is where the CPU accesses the data from.
Thank you. As I said, I'm not expert in this area. Thanks for your point, Professor. Okay. And for correction. Here, it's their visualization. They said I didn't like their visualization, but let's see what they said about their progress instead of the LoRA. They said in simple fine-tuning, you have an optimizer state that bring back all the gradient to the models and update the weights. So, for example, for 10 billion parameter, you need 160 gigabyte. But they said in LoRA, okay, they do something nice with using less than parameter, but unfortunately they use 16-bit parameter for each weight. We decreased this number to 8 bit per each weight, but we get the same accuracy or even better accuracy, and it's their technique for moving the data between the CPU and GPU. So here is their result. They compare their work with the GPT-3. The percentages shows how much these models can achieve the same accuracy to the GPT. For example, here, their model, which they call it Guanago or Co, I don't know how they spell it, get the 97% same accuracy like GPT. GPT-4 get better than accuracy than GPT-3, it's clear. I think it's really acceptable by using this small portion of the data. For example, look at here. Here, for example, they only use 5 gigabytes of the memory to train the model, to fine-tune the model, and get around 90% accuracy, 87% accuracy, same as the GPT-3 with a smaller number. And I think these results show how much we need to consider their approach during our fine-tuning tasks. Finally, we have DoRA, and last one. I think this one is really interesting idea. I saw their idea in several different projects. Also, Professor, if you remember, during the forward Professor by the Hinton, they used the same idea. I think their mathematical idea was really simple, but it was really awesome. Okay, we have a vector here. They said, what is the vector? What can we understand when we see this vector? You know, everyone says, okay, it contains some information, or it can be a dot in high dimensional area, space. So what is this vector? What can we solve by this one? They said two main things that we can understand. First one is that the magnitude, the other one is direction. These two information is really necessary when should be the first thing that that come in your mind when you look at the vector. Because if it's the point, it's not only the point, it's a magnitude from the center and it's a direction. Show the direction, okay? So how can this one magnitude and direction? How can this knowledge can help us to improve the fine-tuning process? When we have a matrix like W, we can extract the magnitude and we have the vectors. Imagine it's the vector. You can extract the magnitude, which will be a number, and you still have your vector. For example, this vector is 2, 1, 5, 6. If the magnitude be, for example, I don't know, 4, which will be only a number, but the direction has the same size. It should be something like 3.1, 3.2, or blah, blah, blah. It will be between 0 and 1. For weight matrices, this happens again, similar. When you have a matrix weight, it means when you have a matrix, if each column is a vector, finally you have a vector of magnitude and you have a matrix for directions. Remember that, okay? The idea is that we extract the information of the magnitude from the matrix. Now we have a direction of the weights. Let's apply LoRA on that weights, on the direction matrix instead of the magnitude. Really simple. Just divide it and same idea. They had a hypothesis, what was really interesting. They said this formula, and I will show something in next paper to you. They said, let's figure out the differences between magnitude and differences between direction in each phase during the fine-tuning. You know, for example, you have the first magnitude, it's the first step without training. After first phase, they calculate the magnitude and find out how much they are different with each other. They do the same for the weight. You have the direction, okay? Direction similarity between the vector calculated by the cosine similarity. They said, okay, we have two matrices which will contain several directions. Let's find out after fine-tuning phase how much they change and visualize these changes. Weight decomposition. It's their result. And I think we need to do such a thing in our works. It's really simple to be applied. Here is a full fine-tuning result at the left. Here is a LoRA visualization. What's these dots? Each color shows different layer. Y shows the change in magnitude. Direction shows change in the, Y shows the changes in direction. And the shape shows the step of the fine-tuning. For example, this circle shows in step 2 of the fine-tuning, in layer 6, the relation between the magnitude and direction is here. And what you generally see, you can see there are an inverse relationship between the magnitude changes and direction. And also you can see how much they are distributed around the mean line. But in the LoRA, it's totally different. All of them are straight in one line, and the correlation between the direction and magnitude is positive. So they said maybe it's not what should be in the real world. So let's extract the information, and they prove it by mathematically in their paper how much it's important to extract these two value, magnitude, and direction. And in effect of the training phase, you can go if you're interested to see the detail. But the result, the assumption was really correct, and the result shows how much it's possible to change the shape of the fine-tuning differences between magnitude and direction during fine-tuning phase.
Is the magnitude M fixed during training?
Magnitude is changed. It's a good question. Yeah, both. Yeah, exactly. With the back propagation, they extract this. It's exactly what I want to say. Okay. Again, weight of matrices we have. They decompose magnitude from the weights. So it's the magnitude, it's the weights. They only train this one simply like a fully connected layer. Do you remember we have a one vector? It's like something like that. They train this one during the back propagation, and instead of training this one, they replace it by the LoRA cells. Simply dividation and replacement. So what was the result? The greens shows the weights that will be fine-tuned. Okay, let's go ahead. And now you can see the changes. The DoRA shows and mimic a better way the fine-tuning, full fine-tuning approach, and they show it's the reason why we can have a much better result than LoRA. Here is the result and how they compare it with the LoRA. The first thing is this column, the number of the parameter. In LoRA with rank 4, they have 10% of the parameter of the model. You have here 11%. Here they have 21%, you have 22%. I think maybe you notice there are 1% more information here. It's because of the magnitude vector. They add one vector instead of the LoRA. So they add 1% weights that need to be updated during the fine-tuning, but look at the result. For example, with rank 4, with this data set, they look at the accuracy that they achieved. 51% compared to the 2.1. And the average, finally, the average show how much their result perform better than the LoRA technique. So I think using the DoRA, which I go through their GitHub and the other stuff, all those three techniques is really available and you can use them. But using the DoRA is really affordable, I think. And it's more accurate. And finally, you can see how much by decreasing the rank of the LoRA cell in DoRA save the performance better than the LoRA. And yeah, thank you. Thanks for your attention. If you have any question, I will be happy to